Hello everyone, thanks for joining us today. In this presentation, we are going to give you an overview of the performance-based design criteria in Canadian Highway Bridge Design Code, which is CSA-S6. It's a joint presentation by me and my colleague, Professor Stavroula Pantazopoulou, who is sitting over there from York University. So this is the outline, give you a brief introduction, talk about seismic hazards defined in the Canadian Highway Bridge Design Code, and then I'll briefly introduce what are the seismic performance categories and their analysis requirements. Then I will talk more details about the various performance criteria and their respective damage states, and finally conclusion. So, you know, when I'm talking about the codes, there will be no results analysis, so it will kind of boring. So please bear with me, okay? Performance-based design was first introduced in Canadian Highway Bridge Design Code in 2014. So the intention was to ensure that the structures meet certain performance objectives under specific seismic hazard levels. And this performance-based design is mainly required for areas where there is moderate to high seismicity. So when in 2014 the performance-based design code was introduced and talking about different kind of performance criteria, there were, of course, some confusions. What we observed that the practitioners were not ready. They did not have the required tools. But at the same time, many people's researchers who started going into practitioners, they had the required tools. For example, if you want to do moment curvature analysis, understand, do nonlinear inelastic pushover analysis, many people had required tools. So in Canada, West Coast is quite seismically vulnerable. So practitioners in that region and academics pursued substantial amount of research study to understand how those performance criteria make sense when you are going to design structural elements. Are they practical or are cost effective and whatnot? So based on those substantial amount of studies, engineers and geoscientists of British Columbia published a report called Performance-Based Seismic Design of Bridges in BC, which is actually available free to download. Based on those suggestions, recommendations, in 2019, some of the performance criteria were updated so that they are practical as well as economic. Now let's look into the code. What it says that the seismic design of bridges should be carried out using the performance-based design. And of course, you have to meet the structural, functional, and service performance criteria under specified seismic loads. And you can also use force-based design, but only for limited cases. What are those? I'll later on show you. Then it says earthquake load effects for capacity protected elements shall be determined based on the elastic design forces or as per capacity design principles resulting from inelastic actions. So, and also it says there are three performance categories. Those are defined by the owners. These are Lifeline bridges, major route bridges, and other bridges. In Canadian Highway Bridge Design Code, the seismic hazards that have been adopted from National Building Code of Canada, where the peak ground acceleration, peak ground velocities, and spectral acceleration responses, these are all actually determined for the site class C, which is the reference ground conditions. Site class C means the very steep soil and soft rocks. So these are determined for periods of 0.2 second, 0.5 second, 1 second, 2 second, and 10 seconds. And these are determined for 3 hazard levels. These are 475, 975, and 2,475 return period. These are for performance-based design. But if you want to do force-based design, then the forces needs to be calculated based on 2,475-year return period earthquake. And since these are for reference ground conditions, if you have different site soil class, then you have to adjust those factors. And in terms of vertical target response spectrum, it says like many of the codes, of course it depends on the site condition and site period. If the information is not available for your vertical target response spectrum, you have to consider 2/3 of the horizontal spectrum, okay? And if the information is available, those values or ordinates that you're taking for your vertical target response spectrum, they should not be less than half of the horizontal spectrum. If you have any questions, please feel free to ask me. Or is it at the end of the session? We will have one question at the end of the session. Only one question, okay. And then the others. Okay, Thank you. Okay, so the government of Canada actually provides certain tools to determine the seismic hazard level. So here I'm demonstrating, if you go into this link, then it will take you to this seismic hazard toolbox where you can choose what kind of site class you have, and then here you can choose the location. Okay, here I'm showing in UBC Vancouver what would be the seismicity. Okay, Vancouver is one of the most seismic active zone, or you can choose current location or latitude longitude, and then you search the address. Once you find out, then you can click on the obtain seismic hazard values. Then it will generate all the results for you, detailed. You know, like a lot of details are here, but I'll just focus on here. Like here, it is showing the uniform hazard spectra. These are for 3 different return periods of earthquakes. It is providing you the spectral acceleration with respect to the time period. In performance-based design, you may have to perform nonlinear time history analysis. For that, you need input ground motions. And these records you have to choose based on the technical environment representing of that location, earthquake magnitude, type of faulting, source to site distance, and local site conditions. You have to choose at least 11 records or more. And then when you have a suit of ground motion, then you have to choose the mean response quantity for your design. Those records, of course, needs to be matched with the target spectrum, and NBC, National Building Code of Canada, prescribes the methodology for that. Again, for input ground motions, the minimum peak vertical acceleration, it says should be taken 2/3 of the peak horizontal acceleration when you are doing analysis only in the one horizontal direction. If you are doing analysis in orthogonal pairs of ground motion records, in that case, the minimum peak vertical acceleration will be 2/3 of the higher of the peak accelerations. When you have site located near to a fault, in that case, what you have to consider, vertical ground motions may exceed the horizontal ground motion in those cases. Then site-specific vertical acceleration records shall be used for such cases. Now, in terms of defining the seismic performance categories, there are 3 categories, 1, 2, and 3. They are based on the fundamental period of the structure, importance category, and also the 2% probability of exceedance site-specific spectral acceleration. And when you have, say, bridge longitudinal direction and transverse direction, you find 2 different seismic performance categories. The higher one will be governing. So this table shows you the seismic performance category, how it is defined. As I said, it depends on the period of the structure, and it has 2 categories, like smaller than 0.5 second or larger than 0.5 second, then 2% probability of exceedance spectral acceleration values, and then based on the importance category, either lifeline bridges or not, based on that, it defines what category it is. When you have low seismicity on both cases, you can see for less than 0.5 second or larger than 0.5 second, your seismic performance category is considered 1. 1 means seismicity is very low, and 3 means the highest. So as you can see from the presentation, that when you have larger than 0.3, in that case, when it is more than 0.5 second, it is seismic performance category 3, and so on. One important thing to note that for lifeline bridges, even though if it is seismic performance category 1, you have to provide detailing of your structural elements as if it is seismic performance category 2 as a minimum. So since seismic performance category 1 is not that high seismicity, it does not require you to do seismic analysis, okay, irrespective of the importance and geometry. And for all seismic performance categories, it says when you have end diaphragms in girder bridges, it shall be designed as an elastic element, okay, except for ductile diaphragms. In terms of analysis requirements, there are provisions for single-span bridges and multi-span bridges. When you have single-span bridges and you have seismic categories 2 and 3, and your skew angle is less than 20 degrees and maximum subtended angle 30 degrees, in that case, you don't need to do seismic analysis. All other single-span bridges, you have to analyze as specified for multi-span bridges. When you have single-span truss bridges, in seismic performance categories 2 and 3, they shall be designed using force-based design method, or you can also use performance-based design. the next one is about this is showing, where you can use performance-based design and force-based design for multi-span bridges. However, performance-based design you can apply for all cases, okay? If you look into here in this particular table, you see that for seismic performance category 1, again, all these multi-span bridges, no seismic analysis is required. When you have lifeline bridges, irrespective of whether it's irregular bridge or regular bridge, you have to do performance-based design. For major rod bridges, for irregular bridges, for seismic performance category 2 and 3, you have to do performance-based design. For regular, force-based design is allowed. Only for irregular other bridges, you have to do performance-based design. There are 4 types of analysis that are mentioned in the CSA-S6. Elastic static analysis, elastic dynamic analysis, inelastic static pushover analysis, and nonlinear time history analysis. So I believe all of you are familiar with those kind of analysis. I don't have to go into the details. Now, in terms of minimum seismic analysis requirements, in terms of what kind of analysis you have to do, it is again depending on the seismic performance category and the importance of the bridge and whether it's regular or irregular. If you closely observe, you can see that for irregular lifeline bridges, only this group require nonlinear time history analysis. Okay, others they do not. And when you have lifeline bridges and major rod bridges, only for irregular you need the inelastic static pushover analysis. And when you have seismic performance category 3 for regular bridges, you need inelastic static pushover analysis. And for other bridges, if it is irregular, you need inelastic static pushover analysis. The previous table was for 975 years and 2,475 years of probability of exceedence. When you have low seismicity, means 475 years of return period. In that case, you don't need to do any inelastic analysis or nonlinear time history analysis. In that case, either elastic dynamic analysis or elastic static analysis needs to be performed. If you see here closely that all lifeline bridges, you have to do elastic dynamic analysis. Major rod bridges, only if it is irregular, you have to do elastic dynamic analysis. Now, when we talk about regularity and irregularity, so how they are defined. So this table shows you how the regular bridges are defined in terms of criteria are maximum skew angle, maximum subtendon angle, maximum span length to ratio for adjacent spans, and then bend or pier stiffness ratio from span to span, okay, excluding abutments. And they depend on whether you have restrainers for continuous superstructure or multiple span, and without restrainers or a continuous deck slab. So another important thing is, if the number of span exceeds 6, then again it is considered irregular bridge. So in performance-based design, we have to make sure that whatever the performance criteria are provided, this needs to be met. Sometimes you may have to use proprietary products or pre-engineered structures. Then in that case, vendors must provide documented evidence that they meet the performance criteria, and the structural engineer also needs to verify that the performance objectives are met. When you have lifeline bridges, at the discretion of the owner, you may require need to do independent peer review or other specific requirements. Structures where they are supporting signs for road direction or they are spanning a roadway, you have to ensure that they should not fall or collapse at the highest seismicity, 2% probability in 2% in 50 years probability of exceedance. Now let's look into what are the performance levels and their corresponding damage states defined in the Canadian Highway Bridge Design Code. So the first one is immediate, and their corresponding damage state is minimal damage, which means that bridge shall be fully serviceable for normal traffic, and repair work does not cause any service disruption. The next one is limited service, which is corresponding to repairable damage. Bridge shall be usable for emergency traffic and be repairable without requiring bridge closure. At least 50% of the lanes, but not less than 1 lane, shall remain operational. If damaged, normal service shall be restored within a month. The other one, next one is service disruption or extensive damage. Bridge shall be usable for emergency traffic after inspection. A bridge shall be repairable. Repairs to restore the bridge to full service might require bridge closure. The last one is the life safety, probable collapse, probable replacement. The structure shall not collapse, and it shall be possible to evacuate the bridge safely. So now, these again now showing all those performance level and their corresponding damage states, like how they are related with the importance of the bridge and seismic performance, seismic hazard level. So when you have the highest seismic hazard level, 2% in 50 years, for lifeline bridges, the service level should be service limited and the damage will be repairable damage. And for major out bridges, it will be service disruption and the damage corresponding is extensive. And for other bridges, life safety and probable replacement. Now, how do you assess what performance level the bridge has? So, of course, you need to do either nonlinear time history analysis or inelastic static pushover analysis. When you are doing that, for the first two service level, you can use nominal resistances, but however, when you are doing the worst case scenario like extensive damage and probable replacement levels, then the resistance behavior, you have to consider it using the expected material properties while you are finding the resistance. For seismic design of lifeline major earth bridges in seismic performance category 2 and 3, you have to consider aftershock effects. However, the code does not provide enough guidance how to do that. Okay? So now I'll go into the details of, how do we understand the various level of damage. So in general, for damage states, when it says minimal damage, it means the bridge remains essentially elastic with minor damage. Damage does not affect the performance level of the structure. The repair damage means some elastic behavior and moderate damage might occur. Primary members shall not need to be replaced and be repairable in place. Primary members capable of supporting the dead load plus live load corresponding to the service performance criteria during repairs. And extensive damage means inelastic behavior is expected. Members might have extensive visible damage such as falling of concrete, buckling of braces, but strength degradation shall not occur. Members shall be capable of supporting the +1 lane of live load in each direction, mainly for emergency traffic, including P delta effects without collapse. And probable replacement means bridge spans shall remain in place, bridge might be unusable, and might have to be extensively repaired or replaced. The next one, we define the damage states with respect to the concrete structures. Minimal damage means the concrete compressive strain shall not exceed 0.006. Reinforcing steel strain shall not exceed 0.01. When I was referring to CSA previous version, S6 2014, 1 minute left? Oh, I have so many other slides to discuss. Oh, okay. So, yeah, you can see like how they have been defined for concrete structures, and we also have various strain limits for steel structures, and it also in terms of buckling requirement, whether it should have local buckling, global buckling. So then we also have performance limit states for connections, bearings and joints, restrainers, and also for foundations. Then the last one is the structural displacement. So we don't have much time. So performance-based design ensures bridge meets safety functionality goals. CHBDC provides structured seismic design approach, seismicity, bridge importance, regularity, determined analysis methods, and performance criteria. When the first performance-based design was introduced, the practitioners, many of the practitioners were not very happy because they did not have adequate training and tools. Now, over the years, through various workshops we have organized, training, now I think our workforce is very good in handling this performance-based design. With that, I'd like to thank you for your patience.